Welcome to Lesson 4 of Module 1.3. In this lesson, we will explore how modern farming is being transformed through precision agriculture, which uses advanced technologies to monitor and manage crop and livestock production with unparalleled accuracy. Precision agriculture is a data-driven farm management approach that uses cutting-edge technology to observe and respond to variability in crops and livestock with pinpoint accuracy. The goal is to maximize productivity and efficiency while minimizing waste and environmental impacts. Precision farming relies on a synergistic blend of data, targeted management, and advanced technology to revolutionize agricultural practices. Data collection means utilizing sensors, satellites, and drones to gather real-time data on soil health, weather conditions, and crop performance. In site-specific management, customizing farming practices for specific field areas, ensuring inputs like water, fertilizers, and pesticides are applied only where needed. Precision agriculture is incorporating GPS, GIS, and Internet of Things devices to monitor and control various agricultural processes effectively. Now, let's break down key components of this system. GPS and GIS systems. These are used for mapping fields and handling spatial data, allowing farmers to manage their land with pinpoint accuracy. With GPS technology, farmers can track where they've applied fertilizer, water, or pesticide, ensuring they only use what's necessary, reducing waste and cost. Let's break down key components of this system. GPS and GIS systems. These are used for mapping fields and handling spatial data, allowing farmers to manage their land with pinpoint accuracy. With GPS technology, farmers can track where they've applied fertilizer, water, or pesticide, ensuring they only use what's necessary, reducing waste and cost. Remote sensing. Drones and sensors monitor crop health, soil moisture, and other field conditions in real time. This data allows farmers to make timely and informed decisions, whether it's watering, pest control, or adjusting planting strategies. Variable rate technology. This is a key technology in precision farming. It uses GPS-guided equipment to automatically adjust seed, fertilizer, or pesticide application based on specific field needs. This technology eliminates the one-size-fits-all approach to farming and tailors every application to the field's unique characteristics. Let's take a look into the benefits and challenges of precision agriculture. Benefits. Increased efficiency. It optimizes resource use, reducing waste and boosting yields through targeted applications of water, fertilizers, and other inputs. Environmental stewardship. It minimizes chemical runoff and pollution by ensuring inputs are applied only where and when needed, fostering more sustainable practices. Cost savings. It reduces operational costs by optimizing input usage and decreasing waste, leading to better financial returns for farmers. What are the challenges? High initial investment. Significant upfront costs for new equipment, sensors, and software can be a barrier, especially for smaller or developing farms. Complex data management. It requires robust systems and expertise to collect, analyze, and interpret vast amounts of data effectively for informed decision-making. Technology adoption curve. Farmers need training and support to integrate and master new technologies, which can involve a steep learning curve and resistance to change. Precision agriculture isn't an isolated field. Its key technologies and practices overlap with other emerging trends in farming. This interconnectedness demonstrates how modern farming approaches shared tools and philosophies to achieve efficiency, sustainability, and resilience. Regenerative agriculture and carbon farming are two related trends that aim to restore ecosystems and help mitigate climate change. Minimized or no tillage. By reducing tillage, we protect soil structure and preserve important soil organisms, linking to healthier soils. This practice also helps with carbon sequestration, storing carbon in the soil rather than releasing it into the atmosphere. Cover cropping. This technique involves planting crops between regular planting seasons to prevent soil erosion, improve soil structure, and add organic matter back into the soil. Diverse crop rotations. Rotating different crops each season helps break pest and disease cycles, promotes healthier soils, and enhancing resilience to weather extremes. Agroforestry. Integrating trees into farm systems helps sequester carbon, improve water retention, and support biodiversity. Managed grazing. Controlled grazing of livestock can improve plant growth and soil health, fostering a more resilient ecosystem. Regenerative agriculture isn't just about ecology. It's increasingly about integrating technology to enhance its impact. Data-driven monitoring. Advanced sensors track soil moisture, nutrient levels, and overall health in real time. Weather prediction systems provide crucial forecasts for planning. Optimized practices. With precise data, farmers can more effectively implement regenerative techniques like no-till farming and diverse crop rotations, reducing disturbance and improving biodiversity. Enhanced ecosystems. These practices enhance soil health, increase organic matter, and significantly boost carbon sequestration, leading to more resilient farms and a healthier planet. By using technology, regenerative agriculture moves from concepts to precise, measurable action, optimizing environmental outcomes and farm productivity. Artificial intelligence plays a crucial role in smart farming. AI algorithms analyze historical data, weather patterns, and real-time information to accurately predict crop yields, potential pest outbreaks, and optimal harvest times. This data-driven approach enhances yield forecast and minimizes waste. AI models utilizing image recognition from drones and cameras detect pest infestations and crop diseases in their early stages. This allows for precise, timely intervention, reducing pesticide usage and safeguarding crop health. Autonomous tractors, drones, and harvesters use AI to automate tasks like planting, spraying, and harvesting. This innovation reduces labor costs, minimizes human error, and boosts operational efficiency in large-scale farming operations. Agricultural robotics are transforming farming operations by automating repetitive and labor-intensive tasks, enhancing precision, and improving overall farm efficiency. Robotic harvesters use advanced sensors and AI to pick fruits and vegetables, significantly reducing the need for human labor. Examples like Octinion's Rubion robot demonstrate precise selection of ripe produce, minimizing damage and boosting quality. Its impact is increased efficiency, lower labor costs, and enhanced produce quality. Weeding robots identify and remove weeds without disturbing surrounding crops, offering an alternative to chemical herbicides. Nio Technologies OZ Weeder is a prime example promoting healthier farming practices. It supports chemical-free farming and reduces labor-intensive tasks. Planting robots ensure high-precision planting, optimizing seed spacing and depth for better crop growth. Eco-robotics, for instance, offers efficient seed placement with minimal resources usage, leading to improved field management. It increases planting precision, reduces seed wastage, and minimizes soil disturbance. These innovations enable farmers to achieve greater yields with fewer resources, addressing critical challenges in modern agriculture. Vertical farming and controlled environment agriculture. What is vertical farming? Crops grown in fully controlled indoor conditions, often in vertically stacked layers. Factors like light, temperature, humidity, and nutrients are carefully regulated by technology. How it works. Plants grow in soilless systems, hydroponics or aeroponics, under LED lights with precise nutrient delivery. Sensors and AI optimize growing conditions, creating an indoor assembly line for plants. Key benefits. It uses less water than traditional farming, requires no pesticides, produces year-round with consistent output, and can be located near urban centers for fresher produce. As climate change poses increasing risks to agriculture, it's vital that farming practices become more climate smart. We can see some examples of water-efficient practices that support these goals. Using drip irrigation or micro-sprinklers, which can save up to 95% of water compared to traditional systems. Employing soil moisture sensors to precisely measure when and how much water crops actually need, preventing over-irrigation. Rainwater harvesting systems, which allow farms to store water during wet periods for use in dry seasons. And of course, cultivating drought-tolerant crop varieties, which can sustain yields even under reduced rainfall. Moving on to adaptation strategies, actions that help farmers adjust to new climate realities. For instance, shifting planting and harvesting times can also help avoid crop loss during heat waves or heavy rains. Integrated pest management, or IPM, becomes crucial as new pests and diseases emerge due to warmer climates. Farmers are also experimenting with alternative forages for livestock to maintain productivity when traditional feed crops fail. In flood-prone regions, raised bed planting can protect crops from waterlogging and soil erosion. The Food and Agriculture Organization defines climate-smart agriculture as an approach that has three main pillars. Increase productivity, ensuring food security and profitability under climate change. Adaptation, helping farmers cope with new climate challenges such as droughts, floods, and temperature fluctuations. Mitigation, reducing greenhouse gas emissions through sustainable farming practices. The CSA involves practices like water-efficient irrigation, using drought-tolerant crops, and adjusting planting times to better cope with extreme weather conditions. These efforts not only improve farm resilience, but also reduce the agricultural sector's contribution to global warming. Let's take a look on advanced irrigation technologies for climate resilience. Drip irrigation is one of the most effective water-saving technologies used in European agriculture today. Instead of spraying water over large areas, it delivers small, precise amounts directly to plant roots. This greatly reduces evaporation and water loss, which is especially important in southern Europe, where water scarcity is becoming more severe. In countries like Spain and Italy, drip irrigation is widely used in vineyards and olive farms, allowing farmers to continue production despite rising temperatures and reduced rainfall. Beyond water savings, it also improves fertilizer efficiency and crop consistency, making it both an environmental and economic solution. Soil moisture sensors help farmers understand exactly when crops need water, rather than relying on experience or fixed schedules. These sensors are placed at different soil depths and provide real-time data, often combined with weather forecasts. In countries such as France and the Netherlands, farmers use these tools as part of precision farming systems to reduce water and energy use while maintaining yields. This is particularly valuable as rainfall patterns become more unpredictable due to climate change. Overall, soil sensors support smarter decision-making and help avoid both over-irrigation and water stress. Rainwater harvesting allows farmers to capture rainfall during wet periods and store it for use during dry seasons. This approach is increasingly common in Mediterranean regions where rainfall is irregular but intense when it occurs. For example, vineyards in southern France and Portugal often collect rainwater from roofs or slopes and store it in reservoirs. This reduces pressure on groundwater and helps farmers stay productive during droughts. It is a relatively low-cost solution that strengthens climate resilience and supports sustainable water management. Integrated pest management for climate adaptation. Integrated pest management, or IPM, is an approach that focuses on preventing pest problems rather than reacting to them with chemicals. It combines different methods such as biological control, crop management practices, physical barriers, and only uses chemical pesticides as a last option. A good example of biological controls is the use of natural predators like labyrinths to control aphids, which is common in European horticulture or greenhouse production. The key idea behind IPM is balance. Protect crops, reduce environmental impact, and avoid over-reliance on pesticides. This approach is especially important today because climate change is increasing pest pressure, while regulations in Europe are increasingly limited chemical pesticide use. Modern IPM is strongly supported by digital technologies. Farmers now use sensors, cameras and drones to monitor pest populations in real time instead of relying only on visual field inspections. In the UK, for example, initiatives such as Agritech East support the use of AI-based monitoring systems that can detect early signs of pest outbreaks. These systems help farmers act early before pests spread widely. The advantage of this approach is that treatments are applied only when necessary, pesticide use is reduced, costs are lowered, and environmental impact is minimized. This makes pest management more precise, more sustainable, and more climate resilient. Climate change is significantly altering pest behavior across Europe. Warmer temperatures and milder winters allow pests to survive longer, reproduce faster, and spread into new regions. For example, pests that were once limited to southern Europe are now appearing further north due to rising temperatures. IPM helps farmers adapt to these changes because it is flexible and data-driven. By combining pests monitoring data with weather forecasts, farmers can predict outbreaks earlier and adjust their management strategies accordingly. This proactive approach is essential for maintaining crop health, reducing losses, and ensuring long-term resilience in European agriculture. Overall, integrated pest management helps farmers respond to climate change by combining ecological principles, modern technology, and smart decision-making, reducing both environmental impact and economic risk. Sustainable energy integration is another key trend in modern farming. Agrivoltaics, the practice of combining solar panels with crop production, is a groundbreaking approach. Solar panels can be installed above crops or spaced among orchards. In fact, if just 1% of EU farmland adopted agrivoltaics, it could generate up to 944 gigawatts of solar power, more than the EU's total 2030 target. Additionally, wind turbines are increasingly used on farms in areas with high wind potential. This provides both renewable energy and income for farmers through feed-in tariffs. Biogas production is another method where agricultural waste like manure and crop residues are converted into biogas for energy. Lastly, energy communities are emerging, where local farmers and residents share ownership of renewable energy installations. This helps build resilient local economies and promotes sustainable development. Social farming is a growing trend where farming activities contribute to the social and therapeutic development of vulnerable groups, such as people with disabilities or long-term unemployed individuals. For example, in Italy, a national law passed in 2015 officially recognized social farming as part of the agricultural landscape. In the Netherlands, there are over 1,000 care farms. Agritourism is another emerging trend, especially in countries like Italy, where agritourismos have become an integral part of rural economies. These establishments offer farm stays, educational workshops, food and wine experiences, and recreational activities. By blending agriculture with tourism, agritourism helps diversify farm income and supports rural communities. The demand for sustainable, local, and transparent food systems is growing. The EU has set an ambitious target to increase organic agriculture land to 25% by 2030. Consumer demand for chemical-free, environmentally friendly products is driving this change. Local food movements are also on a rise. The Chilometro Zero movement in Italy promotes the consumption of locally grown produce, and the Locavore movement is gaining traction across Europe. Consumers today expect transparency. They want to know where their food comes from, how it's produced, and its environmental impact. QR codes, blockchain, and detailed labeling are helping make this possible. Here we're connecting the emerging trend of consumer-driven value chains to the broader concept of multifunctional farming. Today, consumers are not only buying food, they are also concerned about climate change, biodiversity, energy use, and social impact. As a result, farming is no longer seen purely as food production, but as a sector that delivers environmental and social value alongside economic output. This shift is especially visible across Europe, where sustainability standards and consumer awareness are high. One important role of multifunctional farming is carbon sequestration. Farmers actively manage land to enhance carbon capture, turning fields into vital allies in climate change mitigation. These practices turn farmland into a carbon sink, helping to reduce greenhouse gas concentrations in the atmosphere. Farms are also becoming producers of renewable energy. Integration of renewable energy sources like solar and wind on farms contributes to sustainable power grids and reduces reliance on fossil fuels. Another key aspect of multifunctional farming is social engagement and agritourism. Opening farms to visitors provides unique experiences, fosters community connections, and diversifies farms' income while educating the public. Finally, multifunctional farms play a major role in protecting biodiversity and ecosystems. Beyond crops, farms manage habitats, pollinator services, and water quality, enhancing the natural habitat of agricultural landscapes. Multifunctional farming reflects the future of agriculture in Europe, where farms produce food, energy, environmental benefits, and social value at the same time. Ethical considerations in smart farming. As agricultural technology advances, it brings forth crucial ethical questions regarding data, access, and employment that must be addressed for truly sustainable and equitable development. One major concern is data privacy and ownership. Smart farming technologies generate large amounts of data about farm operations, yields, and management practices. This raises questions about who owns this data, how it is stored, and how it may be used by technology providers or third parties. Ensuring farmers maintain control over their data is essential to prevent misuse and build trust in digital tools, as seen in discussions around platforms like Climate Field View. Another key issue is the digital divide. Smart farming often requires significant investment and reliable internet access, which can disadvantage smaller farms or those in less connected regions. This creates the risk that technological progress benefits only a few, widening existing inequalities. Addressing this requires supportive policies and better access to digital infrastructure. Finally, there is the issue of labor displacement. Automation and robotics can replace tasks traditionally carried out by farm workers. While this improves efficiency, it may reduce employment opportunities in rural areas. To manage this transition responsibly, there must be a focus on reskilling workers and creating new roles within the agricultural technology sector. Addressing these ethical dilemmas is paramount to fostering responsible innovation and ensuring that the benefits of smart farming are shared equitably across the agricultural sector. That concludes Lesson 4. Thank you.